All right, stats. So here is section 7.6. We're closing out the chapter on confidence intervals here. Once again, I'm going to write what the two confidence intervals are. P hat, if I'm doing a proportion problem, P hat plus or minus Z star times the square root of P hat Q hat over N. And if it's an X bar, it's X bar plus or minus T star, which took us a little while to uncover that little mystery, over the sample standard deviation over the square root of N. Those are my two confidence intervals. Now this is the write-up of the confidence intervals, so I'm going to talk about the random condition. I'm going to talk about the independent, not the independent condition, that's a different thing, the normal condition. I'm going to name populations. I'm going to talk about what parameter that I'm estimating. Is it a proportion or is it a mean? I'm going to actually find the confidence interval. I'm going to interpret the interval. I'm going to interpret the level. We're going to put all of it together here today. Here we go. A review, the large sample size condition for confidence intervals. For proportions, we are using P hat plus or minus Z star times the square root of P hat Q hat over N. We've seen it quite a few times now. It's that right there. To estimate an unknown population proportion. That's what we're estimating. For the large sample condition, we got to verify that N times P hat is greater than or equal to 10, and N times Q hat is greater than or equal to 10. So that the sampling distribution for P hat, we can say is approximately normal. If we can't say it's normal, we got no business using a Z star because that comes from a normal curve. Okay, that's the condition for P hats. Well, now let's talk about the condition for the sampling distribution of X bar. For means, we are using X bar plus or minus T star times the sample standard deviation over the square root of N, that one. To estimate a population mean instead of a proportion. Decimals, averages, right? For the large sample condition, we can verify in two different ways. We can know that the population is told to us is known to be normal. If that's the case, the sampling distribution is always normal regardless of the sample size. Or bullet point number 2, if N is greater than or equal to 30 and I don't know this about the population, or I know that the population is skewed, when N is greater than or equal to 30, we can use the central limit theorem, which we learned a couple chapters ago now. The central limit theorem, which we always say CLT, to say that the sampling distribution for X bar is approximately normal. So if the sampling distribution looks to be like it's normal, then it's okay for me to use a T distribution to get my T star. But what if neither, I didn't spell the whole word there, I stopped in the middle. What if neither of those is true? There is a third option. If that's not true, and that's not, I don't mean either of these two. I mean within the X bar stuff here, this is me talking about X bars, this is me talking about P hats. Within X bar stuff here, if I don't know the population shape, or I know specifically it's not normal, and the N is not bigger than 30, I do have one more option. With a smaller sample size, smaller than 30, if you have the data, you graph the data. Okay, you can make a box plot out of your data that's given to you, or a histogram. And if it looks like it might start to fill in as a normal looking curve, then we're okay saying that the sampling distribution might be normal. If there aren't any large outliers, if you see big outliers, shut it down, dumpster fire. Or strong skew. If you see strong skew, shut it down. Some skew is okay. Strong skew or outliers, you're allowed to verify that the large sample condition, you're allowed to verify it visually. Okay, so let me get an example and let's see what we're getting into here. I'm going to go to page 485 and it's going to say, are the conditions met? And so we're dealing with X bars and let's see what happens here. Putting it all together, the 4-step process. Are conditions met? Oh, here we go. We're at the top of the page here. Determine if the normal large sample condition is met in each of the following settings. Here's setting number 1. How much force does it take to pull wood apart? Oh, now we're talking. Let's get angry and break some wood. The stem plot shows the force in pounds required to pull apart a random sample of 20 pieces of Douglas fir. Just getting after it. Angry, I'm going to pull some wood apart. I've had it with these people not doing their homework. I'm going to break some stuff. Okay, I look at a stem plot, and you guys, this is clearly strongly skewed, and these are probably outliers. So since this is skewed to the left and with outliers, there's no way I can say that this is a suggestion that the population might be kind of normal, so we're okay using the normal curve. Part A, no, absolutely not. The sample size is small. There's only 20 of them. It's less than 30. And the stem plot shows strong left skewness and possible outliers. So nope, we're out on that one. Part B, suppose you want to estimate the mean SAT math score at a large high school. The box plot summarizes the distribution of SAT math scores for a random sample of 12 students, not big enough to use the central limit theorem. I'm looking at this and I see that this goes further than that one, which is an indication there's a little bit of a pull to the right, slightly skewed to the right. But look, the middle median thing is right in between these. And so a little bit askew, especially with only 12 students, is not so bad, because maybe if I took those same 12 and I added 70 more students, couldn't you kind of see this thing evening out? If that's the case, then what it might be is that the population is actually normal. This is a hint that the population might actually be normal. So we would say yes in this scenario. Although the sample size is very small, the box plot shows no strong skewness or outliers. There's a little, but it's not way out here, and I don't have outliers, and so we're going to be okay with that one. All right, so if we look at a graph, we're kind of taking it as a clue that this might be true. The population might actually be normal. Since we're taking a sample from the population, we haven't taken an average yet, and since we're taking a sample from the population, if it's starting to look like it might fill in like it's normal, then we kind of use this one and say, yep, sampling distribution is going to be okay. All right, page 2. Ooh, there's a blank copy of page 1. You don't need that. We already filled it in. Oh, man, look at all these blanks. We got a lot of work to do, kids. A lot of work to do. Let's go, stats. There is an agreed upon process. An agreed upon process. That shouldn't say from. That should say for. I'm a loser. Writing up statistical inference problems. It follows these 4 steps according to the author. I don't like these 4 steps. I'm going to go Larson style down here. We'll get to that in a minute. The author says whenever you do a stats problem, you should do the state, plan, do, conclude, vibe. That's what our boy Starnes is trying to tell us we got to do. State what your problem is, plan how you're going to fix it, do the math, and then make your conclusions. Okay, describe the problem with context. It's an applied math problem, so if it's about pulling wood apart, we should talk about pulling wood apart. Plan, describe the procedure. In this scenario, I would be making a confidence interval, right? And verify any conditions. Well, there's 2 conditions, the random condition and the normal condition, that apply to that procedure. Actually do the math stuff. That's the actual math stuff you showed up to learn. And then conclude, report the interval and interpret the interval with context. So again, if it's about pulling Douglas fir apart because you're angry with foot-pounds of energy, then you should put that in your interpretation. For us, as far as our confidence intervals go, I'm not going to grade it as a 4-point problem. I got my own system, people. I got my own system. We will include this into our write-up. Ready for this? First step, first point on this problem is name the population correctly, as specifically as you can. Our population of interest is blah, blah, blah. All of the Douglas fir wood in the world. Name the parameter is number 2. Now, you guys, that's got to be either a mean, because we're talking about averages, or a proportion, because we're talking about decimals, of, and then you would put the context in, like pulling Douglas fir wood apart because of your rage problem. Number 3, name the procedure. Okay, we will use a 95% confidence interval is a way to do that. A 95% confidence interval to estimate that mean or that proportion, whichever one we're doing. Number 4, verify the random condition. We've talked about that a few times. Number 5, verify the large sample size condition, which I also frequently refer to as the normal condition, because we're suggesting that the sampling distribution is approximately normal. Number 6, write the formula for that confidence interval, fill it in with numbers for a different step, and then give the resulting 2 numbers as your last step. And then number 8, you will interpret the interval. Hey, we are 95% confident that the mean amount of foot-pounds per square inch that it takes to just massively rip apart wood because you're angry and you have a rage problem is between a little number and a big number. You guys see how that goes, right? A little number and a big number. Okay, so here's how the way I grade this. It's gonna be an 8-point problem on the test, you guys. That's how I'm gonna grade it. So here's how it kind of goes along with this. When it says state the problem and do it with context, for me, that's numbers 1 and 2. State the problem, name the population, name the parameter that we are going to talk about. I'm a little more specific than this vague stuff here, and I'm going to give you this as an outline when you take the test. So you don't have to memorize all these. You just got to be able to knock them out. The plan part. Describe the procedure and verify conditions. For me, that's numbers 3 through 5. Look, I'm going to say what procedure I'm doing. I'm going to do a confidence interval. I'm going to talk about the random condition. I'm going to talk about the normal condition. The do part, the mathy part, is 6 and 7. Write the formula, write the numbers, give the result. And then the conclude part is where I interpret the interval at the end. Now notice what I've done here. I really did leave off number 9, where you would interpret the level, because you're probably tired of writing at that point. Let's be honest. Okay, so I'm going to flip the page and look at this hot mess right there. That's not a whole lot of typed words, people, and that's an awful lot of line space. Let's go to page 485, and let's do a write-up, yo. Toilet paper. My girls Christina and Rachel randomly selected 18 rolls of a generic brand of toilet paper to measure how well this brand could absorb water. To do this, they poured a quarter cup of water onto a hard surface and counted how many squares of toilet paper it took to completely absorb the water. What a couple of losers. Here are the results from their 18 rolls. Now, see, this is new. I don't think we've seen this before. Now I gave you all the data. So you don't have X bar and you don't have a standard deviation. You got to put them in the calculator and find them. Then it says construct and interpret a 99% confidence interval for mu, the true mean number of squares of generic toilet paper needed to absorb a quarter cup of water. That's got to go in my calculator, and I've got to follow those 8 steps to write this whole thing out. So let's race. You guys, get your calculadora. I'm going to hit stat, and I'm going to clear out my list. You guys can pause the video if you need to and get your calculator. I'm going 29, 20, 25, 29, 21, 24, 27, 25, 25. Nope, that's wrong. Dang it, went too fast. 27, 25, that's a 24. 29, 24, 27, 28, 21, 25, 26, 22, and 23. I went pretty fast. I should probably double check those because I am kind of a loser. 29, 20, 25, 29, 21, 24, 27, 25, 24, 29, 24, 27, 28, 21, 25, 26, 22, and 23. Nailed it. There's, if you look, it'll tell you how many data values you have. So I go up to the last one. I have 18 of them. And they said this is 18. Now, I'm going to get this out of the way. And we're going to do this whole write-up. You guys ready? You got what it takes? Make sure you sharpen your pencil. Here we go. You know what? I got my notes that I watched, so I want to show you. Step number 1, name the population with as much context as you can. So step number 1, name the population. Here you go. You ready? Our population of interest. Use that phrase every time to start this off. Our population of interest is all rolls of generic toilet paper. Do these 2 losers really sit in somebody's kitchen and pour water on the counter and then count how many squares of toilet paper? I mean, honestly, you got nothing better to do. Anyway, there we go. There's our population. It's all rolls of this generic toilet paper. Thing number 2, name the parameter. Are we looking for a mean or are we looking for a proportion? This is the number of squares it takes, and they're finding the average. So let's see, we will estimate the mean number of squares it takes to soak up a quarter cup of water. To soak up 1/4 cup of water. Okay, so I've mentioned my population, I've mentioned my parameter, and you have to use the word mean or proportion. It's either an average problem or it's a decimal problem. You got to get that right. Now I go to number 3, name the procedure I'm going to do. Well, they asked me to make a 99% confidence interval, so we will estimate that mean. We will estimate that mean with a 99% confidence interval. All right, there's the first 3, and really the way to remember them, I mean, I'm going to let you use the outline of the test, doesn't matter, but they're all P, population, parameter, procedure. Okay, then let's see, we will estimate that mean with a 99% confidence interval. So my population is all this generic toilet paper. My parameter is the mean number of squares it takes, the average number of squares to soak up this much water. And what am I going to do? I'm going to make a 99% confidence interval to estimate that mean. So I named the population, the parameter, the procedure, and now I got to verify the random and the large sample size conditions. Well, it says that they took a random sample of 18 rolls of toilet paper. Okay, they took a random sample of 18 rolls. I'll just put rolls. You guys get what that means, right? Now the large sample size. We don't know the population shape. We don't know the population shape, so that's not good. And n equals 18 is not large enough for the central limit theorem. All right. However, we can take a look at the graph. So I've got all these numbers in here. Let's look at a histogram and see if it looks kind of, single peaked and symmetric, or does it look like it's got big giant outliers and skew? Let's take a look. So to look at a graph, it's been a little while since you did this. You hit second and y equals. That's the statistical plot menu. You hit enter to turn a plot on. Make sure that your cursor's on and hit enter so you can plot this thing. Go down and move over to the histogram. That's the one that it's the easiest to see the shape. So I would just use that every time. The box plot's okay, but I would use this every time. So hit enter, and then my stuff is in list 1, leave the frequency as 1. And so I'm ready to take a look at this thing. First, I'll just go to y equals real quick, and if there's anything in there from an algebra class, get rid of it. And then I'm going to go zoom, and then stat is number 9, zoom 9. And there's my histogram. It doesn't look perfectly normal. There's a little gap here and there's sides out here, but I don't see anything that looks like it'd be an outlier. And I don't see any reason to call this really skewed either. It's kind of symmetric. So I think you're good right there. You don't have to do anything else. But I'm going to look at a box plot also just so you see it. So I'm going to hit second and y equals, and I'm going to hit 1 for plot number 1, and I'm going to change this to that box plot right there. So I hit zoom and 9 again. And you see, it doesn't really show anything that suggests it's really crazy skewed or there's outliers. So we don't know the population shape, and n equals 18 is not large enough for the central limit theorem. However, a histogram of the data, there's our phrase right there, a histogram of the data, what did it tell us? It shows no skew or outliers. Oops, misspelled that. No skew or outliers. So the normal condition is met. Normal condition is met. Okay, guys, it's time to do some math. However, a histogram of the data shows no skew or outliers, so the normal condition is met. Let me run them down again. Population, toilet paper. Parameter, average number of squares. And so the procedure, we're doing 99% confidence interval. We verified the random condition with a random sample. We verified number 5, the large sample size or normal condition, by graphing the data and seeing no outliers or strong skew. It's time for formula, numbers, and result. We've been doing this part for a while. Our 99% confidence interval is, here you go, formula, x bar plus or minus t star times the sample standard deviation over the square root of n. Numbers, well, I need some numbers here. So I'll go back to my calculator, and there's my list. Oops, there's my list. But if I hit stat and go over to calc and do one variable statistics with my list 1, I get all the stuff I need. The mean is 24.9. So I'm going to go 24.9 plus or minus. I need a t star. I could look it up in the chart if you guys want to look it up in the chart, or I could do it on the calculator. Not everybody has inverse t on their calculator, so I'm going to go to the chart. So I'm getting in the book, and I'm going to get to the right page here. It's a 99% confidence interval. Let's put that right there. 99% confidence interval. There it is. And my sample size was 18, so I go up until I'm not 18. You got to subtract 1 and go to 17. So it's the second row in this white part right here. 99%, 2.898. That's my t star. 2.898. 2.898. And then it will be times the sample standard deviation. I get that from my calculator. There's the mean. The sample standard deviation is this S sub x. It's 2.86. We're going to go 2 decimal places. 2.86. 2.86 divided by the square root of my 18 rolls. Now you subtract 1 for degrees of freedom to get here, but you put the actual n in there. All right, go to my home screen, and I'm going to put the stuff in and get my confidence interval. 24.9 minus. Always do the minus first. You start with the lower number. 24.9 minus 2.898 times 2.86 divided by the square root of 18. That's it. It all goes in one entry. Hit enter, and I get an interval of 22.95. And then let's do the same thing, but hit plus. Now, I don't have to type all this in again. I'm going to hit second and enter, and it brings this back up. And everything else is the same. I just got to change this to a plus. Why type it in again? You know what I mean? So then I get 26.85. Okay. Let's go back to our outline. I named the population. I named the parameter as a mean. I talked about the procedure. I'm going to do a 99% confidence interval. We verified the random condition. We looked at data to verify the normal condition. I wrote down the formula. I looked up a t star, and I looked up my x bar and standard deviation. I got my numbers. I put them in the calculator. I got a result. Last thing I got to do is just interpret my interval. Okay? We are, hell yeah we are, 99% confident that the true population mean, got to put the context in here, guys, number of squares of generic toilet paper that it takes to absorb a 1/4 cup of water. Ooh, that's a big sentence. We are 99% confident that the true population mean of number of squares of generic toilet paper it takes to absorb a 1/4 cup of water is between these two numbers, 22.95 squares and 26.85 squares. We're pretty sure that the population is in between there. We're 99% confident that the population number of squares it takes to soak up a 1/4 cup of water. Now, here's my bigger question. What are my girls' names? Christina and Rachel. Sooner or later, your parents are going to come home and notice that you have 18 rolls of toilet paper and you've been taking squares off of each one of those. and trying to soak up this water, and now you got 18 half-used rolls of toilet paper all over the kitchen. That's probably going to be an uncomfortable conversation. That's all I have to say. Is your parents are probably not going to enjoy that. All right. I'm going to leave you guys with a couple of problems to do. I'm going to have to put them on Canvas because I don't have them written down right now, and I don't want to just make them up while I'm talking on the video. So 7-6, day 2. I'll show you the notes. This is what we're going to be doing. Ready for this? 7-6, day 2. I'm just going to go through examples. So we're going to go find a problem. We're going to do the population parameter, procedure, random, normal, formula, numbers, interval, and interpret. Then I'm going to go over here, and we'll do a whole write-up. Then I'm going to do another one where I go through all the prompts and get through every one of them, and then we do the write-up. So the next section, here's what I'm probably going to do for my video. I do one, and you do one. I won't do the video for this page right here. I'll post my answers, but you do it and then see how well it goes. And then I do one, and you do one. And I probably won't even assign any homework out of that. If you guys can do that right, you're probably doing okay. All right, that's our video for today. We'll see you guys tomorrow.